Our homes and electronics may have become more energy efficient, and advancing technologies like wind and solar power have seen big gains over recent years, but there remains a surging power demand. In America, tech giants operating data centers and AI systems are fueling the calls for more electricity, with the U.S. Energy Information Administration projecting a 2.4% increase in demand for 2026. That may not sound like much, but it's more than double the average growth rate of any year in the past decade. In 2022, the Lawrence Livermore National Laboratory made history, demonstrating for the first time in a lab setting fusion ignition. And just this April, an experiment at the National Ignition Facility achieved ignition for the 8th time, producing a record fusion yield of 8.6 megajoules from 2.08 megajoules of laser energy delivered to the target. Dr. Mike Campbell is president of MCM Consultants and an internationally renowned expert in inertial fusion, and physicist Omar Hurricane is chief scientist for the Inertial Confinement Fusion Program at the Lawrence Livermore National Laboratory. With their insight, we'll take a look at the progress made in this field, compare U.S. ambitions to that of other nations, and learn exactly how close we are to commercializing fusion energy. That conversation is next.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more. Today's episode is also brought to you by American Elements, the world's leading manufacturer of engineered and advanced materials. With a catalog of over 35,000 products available in both industrial bulk and laboratory quantities. To learn more, visit AmericanElements.com. American Elements. Now invent.
From Photonics Media, this is All Things Photonics, a podcast where we explore industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, we'll speak with some of the brightest minds in industry and research about the trends shaping the landscape of photonics.
Gentlemen, we're at a special moment in time where advances in science and technology are creating an increased demand for power, and these advances are also offering a path to commercial fusion energy. Is there a single approach or system design under the umbrella of inertial confinement fusion that's emerging as the most viable for commercial efforts?
So my view, and Omar, please chime in, is that we're at such an early stage of this. There's been great scientific advances, in inertial fusion, particularly that's been done at NIF. It's demonstrated. I'd like to say that from a scientific standpoint, the demonstration of a burning plasma is really has never been done by any fusion approach, to date after all this many decades. And so inertial fusion is in a very good scientific position, but the technology to make it commercial is a great challenge. And my belief is that given that where we are right now, down selecting to any one approach or company is premature. We need to be able to support the ones that have credible target designs, target physics, and that go along with a credible driver. We need to support the companies, both publicly and privately, that go along those lines. But I think, from a scientific standpoint, the idea that you can implode a target, get fusion to go, like has been demonstrated at NIF, and Omar was very much involved in that, and other people at Livermore, is really, really a very big step in the credibility of ICF moving forward. Omar, do you want to comment upon that?
And I basically agree with Mike. What we did at NIF is we now have an existence proof that it's possible to get this to work, but it was a very scientific demonstration, and it's not really practical for just, throwing energy on the grid. Technically, every inertial confinement fusion approach has pros and cons, and those competing factors do make it difficult to just choose one as the clear winner. Even the one that actually just demonstrated a burning plasma and ignition and target gain, it's not necessarily clear that's the winner. And so the way I like to describe it to non-specialists is that we would be foolish at this point of time to take all of our money for retirement and put it in one stock in the stock market. Instead, you want to diversify. And I think the same is true of inertial confinement fusion, and in fact, all fusion approaches. because they all have different pros and cons, and it's just too early to pick the winner.
Gotcha.
I
So
think
oh, sorry, go on, Mike.
no, I think what Omar said exactly right. But to get started, any fusion company has to have, number one, a credible target concept, right, that is physics-based. And secondly, it must be able to, in principle, achieve the gains you need with a driver, be it a laser or a pulse power, that is credible. And if I need the Death Star to make fusion work, it doesn't make any sense, right? And so I think, any company that has both of those two criteria is ones that, we should support. And as Omar said, it's, it's been a science program, and there's never really been an IFE federally funded program of any scale for years. This never has been. And so all the technology and the engineering science to make ICF, IFE, a commercially credible approach, has been lacking. So hopefully, all this investment that the private sector has done as it goes into this will hopefully move that forward. And I know the federal government is reevaluating that. Well, we should look at IFE because they really have not. I mean, there's some advocates in there, but historically, it has not been. The U.S. federal program has been focused on magnetic fusion, primarily tokamaks, which is has its pluses and minuses, like Omar said, all fusion approaches. But expanding it to include IFE concept is something which we're all hopeful to see.
And talking about kind of and not just federal involvement, but private sector as well. We've seen some significant investments in fusion, over the past few years that are keeping the momentum going. But it's kind of a two-part question: is it enough? And is there something more that the fusion community can do to get companies or maybe federal funds involved to bring more funds and just more awareness to this sector?
I think, to make fusion a reality, it's going to require billions of dollars, to be able to get a fusion power plant that is commercially viable. And so finding the private sector to do that, Commonwealth has been a good example. They've raised $3 billion effectively. ICF is going to require that amount of money also to be able to take it to the point of commercial viability. And my view is that one of the things that we should look for areas that are common problems for whatever ICF approach you have. If you're going to do deuterium tritium fuel, breeding tritium, recovering tritium, how you deal with plasma phasing components, when there's common things, target fabrication, when we can find some common areas to have companies work together, not just in competitive things, but actually in common areas, is something which we've got to try and strive to do and get the federal government to be supportive of something like that. Omar, what's your thoughts?
I do wish more of these fusion companies would work together and collaborate on topics of common interest, because fusion isn't cheap and it's going to take an enormous amount of resources to solve the remaining scientific and engineering problems that are needed to be solved in order to make this practical. The government is really fond of what they call public-private partnerships right now. And I think that's a way to leverage private money so that the government doesn't have to put in that much. But what we've seen with the work we've done on the National Ignition Facility, it really does take a significant amount of government investment over a sustained period of time to be successful. I mean, Mike was involved in the origins of the NIF, which go back to maybe the late 80s, early 90s. It took that amount of time to go from the vision of doing this thing and building it to actually having construction done in like 2009, starting experiments, finding out things weren't working quite as expected, and it took another decade of time after that to actually get to the burning plasma and ignition and showing target energy gain. So this is a long duration problem that requires a lot of resources over a sustained period to do in any serious way. People need to understand that.
I think, Joe, it's a good question because, how do you get the federal money and the private to work together? And I think finding, as Omar said, and we said, common areas. It's like ICF, target fabrication is a big deal. I mean, we need, if I'm doing an ICF, an IFE plan, I need tens to million targets a day. And they have to be cheap and they have to be able to, and they work. And so finding ways of doing that, finding, technologies and companies working together is common to all. And so the more that we can encourage those is another thing. And again, I think tritium is a story that needs to be much more talked about. and common areas to work on. So, but it's going to take time. I mean, fusion energy is not a scientific endeavor; it's a commercial endeavor. And the other thing I think we'll talk about supply chain, which is a major issue, also is moving forward on this. But I think you need sustained effort, and it's going to cost you billions of dollars by the time you actually get energy on the grid from fusion.
So I know you both know the gains that could be made when we eventually reach this point. And we talk about the importance of more funding. It's going to take billions. So then, can you give me the sales pitch? If I am the federal government, or if I'm just big business investor with just billions in my pocket, what is the elevator pitch to say it's worth giving this money to something that will promote fusion?
Fusion is the ultimate energy source. It can be located any place you need it. It's dispatchable 24/7. It can produce a range of energy products from electricity to process heat, from manufacturing, for desalination, for water. It's inherently safe. It can never have the problems that fission does. It's obviously green, and it's something that the world needs energy well beyond what it needs to do to raise the standard of living across the board and to deal with all the challenges we have right now. On Earth's God's work must truly be our own. Fusion is the way that the nature makes energy. We're going to have to do it here, but it is the ultimate energy source. And I think recognizing that is something that, and it's the elevator pitch that I give. It's going to happen. Fusion will happen. There's nothing in the laws of physics or engineering to prevent it. It's just a dedication to solve these problems and eventually get it to work. Omar, what do you say?
I'm not in the elevator pitch department. But certainly if we don't dedicate ourselves to doing it, it won't happen by itself. And it is, the ultimate source of energy with a lot of advantages. It's not perfect, though, so there are some practicalities that, it's not perfect. So, those have to be recognized and addressed. But if we don't start on this now, it will happen by itself. So
that's safe to say. And Mike, you brought up supply chains before, and naturally this has different impacts on different nations. How do we view the idea of fusion being pursued as part of the national strategy here in the U.S. and how does that compare to other nations' fusion ambitions? Maybe Germany, China, Japan.
Well, I think so. Obviously, it is a national issue. Energy security is national security. I remember I grew up. I remember the Arab oil crisis. After the Yom Kippur War. First thing you have to say, wait, energy is an international problem. It's not just a domestic issue. So it is a national security, and countries around the world clearly are recognizing that. I mean, Europe Germany, got out of fission after Chernobyl and Fukushima. They've, I think, discovered that was a mistake, and now they're pretty gung-ho on fusion. So Europe is moving forward on this. There's great fusion research done in Europe. I mean, but the China has clearly made fusion a national priority. It's clear from all this stuff that you read and see, the intel and everything, China has made it a national priority. And so we are in competition. This is the Cold War was also, when Sputnik happened, it really, wait a minute, this Soviet Union could be a threat because their technology could be better than ours, right? And all of a sudden missiles were something that they could do and we couldn't, or satellites. And so it really was a wake-up moment for the U.S. Look at all the things that happened after Sputnik. China is making fusion a Sputnik moment for the United States, I believe. They're investing in all forms, both magnetic and inertial. They're building a laser now bigger than NIF for the national security applications, but of course it has an energy spinoff. So, it is a national prerogative. And I think when you hear the DOE and other people talk about that, they worry about China and they speak about this. The question is, can we rally public sentiment and the federal and public money to recognize that threat? That do we want to import fusion power from China or technology? Look how many fission plants China's building right now. We talk about SMRs all the time. When's the last one? Let's build one. China's building them, right? And so we have to recognize this is not just a paper tiger. This is not just people being excited about something. It's a real threat. And for national security, we need to be a leader in fusion. And I just hope that our private sector is very robust, and thank God we have that. but it's something that recognizing we are not just going to dominate this field because we think we're better.
I have a slight twist on what Mike is saying. Uh, in a way, what we've done is we've just Sputnik the world because we are the first ones to demonstrate burning
Yes.
plasma, laboratory ignition, target energy gain, and so forth. Remarkable accomplishments that a lot of critics were saying would be impossible to do in the laboratory because of some mystery physics that we didn't know about. We've demonstrated that that is not the case. What could happen, though, is kind of like what happened with Russia and Sputnik and the United States. The Russians were the first ones to put Sputnik in orbit and get into space. The United States followed. The United States went all in to reverse that situation. And I think,
Yes.
kind of like what Mike was saying, China is in that position now. While we might have done it first here in the United States, a lot of other countries want to turn the tables on us, and
Mm.
if they are dedicated enough, they can. Germany has a very serious. Their Germany's not a is an ally, of course, but Germany has a very serious intention to develop fusion energy, and in particular, inertial fusion energy. I've worked on advisory panels for the government, and they are serious about it, largely because of what Mike said. They gave up their fission program and they are in desperate need of more energy. And with the situation with Russia these days, they don't want to be reliant upon fossil fuels from Russia uh, for their economy to function. So they're in a kind of a desperate situation where they must make this work. And so they are accelerating research on it. In China, they have a huge amount of resources. They're doing everything across the board in terms of people and funding and just a government that functions in a way that you don't have lawsuits to try to stop you from doing things. That just doesn't happen there. So we can potentially lose the advantage that we have in the Sputnik moment that we just had in fusion
Mm.
to countries if we don't have consistent support.
Actually, Omar made a good point about that a lot of people did not think NIF would achieve ignition after many years. There was a report by the Jasons, saying it's highly unlikely about 6 months before NIF did ignition. And actually, when I was
As we got
doing, yeah,
and they were changing the wording. It's very entertaining to watch, although that was quite painful.
yeah. And, and when I was doing NIF many years ago, we had a different relationship with Russia than we do today. The Russians had a pretty robust ICF program, and they told me you need a 20 megajoule laser to do ignition in a laboratory. NIF was 2 megajoules. They said it'll never work. So any of those people are still alive, they will say, "Wow, they're a lot better than we thought they were." And as Omar said, the physics, if you have the dedication and not give up when you have obstacles, that's the challenge. That NIF had to overcome. Luckily, the funding kept going, but it was not easy. And so I think, but recognizing that, we're not in this alone, that, Germany is a big, as Omar said, China, to me, if you asked Bob Mumgard at CFS, and he will say they worry most about China. They're building a tokamak similar to Spark, that they expect that will get what NIF did, scientific break even, in a couple of years. So we have to recognize that this is an international competition. And again, anyone who controls energy, look at the influence of the Mideast when they control fossil fuels, how it's had on the world politics and everything else. If you have a country that dominates fusion and can play a game like that also. So it's obviously different than having the natural resources that you sell. But if they have the technology and demonstration and they control what the world does with that, that's going to be something we have to worry about.
Yeah, and I think we've talked about too how we have a long ways to go before something gets commercialized, but it's worth highlighting. The progress, the milestone from NIF in 2022, and then I believe as recent as April, I think it was a 2.08 megajoule laser, yielding 8.6 megajoules, if I got that right. So let's talk a little bit about the progress we've made because we know there's a lot to go, but it's worth taking a pause to say before 2022. Some amazing things have happened.
Yeah. So let me say something. Then Omar, who's very much involved, can say. But fusion, we've known since the early 1950s that fusion works. right? And the question, but the issue always in the laboratory is how small could I make this and it would still work, right? I'm not going to, to give you a sense. If you saw Oppenheimer, a kiloton was talking about a new unit, a kiloton. Well, a kiloton is 4 trillion joules is a kiloton. And we're not going to make kiloton laboratory facilities. And so the question always was, how small could I make it and it would still work? And NIF has demonstrated at the megajoule level, whether it's a couple megajoules or ultimately several times that, I can get fusion to work in the laboratory at a scale that, in principle, is affordable and at a level that can be that can make an attractive power plant. So that progress, it's a remarkable achievement from NIF, and I think it's really again, I will say ICF is the most scientifically advanced fusion concept because it has demonstrated scientific gains of 4, but actually remember NIF has done what's called indirect drive. So there's a fusion capsule inside. That capsule gain is about 33. So the fusion device inside the whole room had a gain of about 33. Omar can talk more about that, but I think that it's just remarkable progress. There's also wonderful work that's been going on in laser development. I mean, I consult for the Department of Defense on directed energy, so I see all the stuff going on in lasers. So there's a lot of progress in both in laser technology. There's a progress in pulse. Other ingredient that's necessary for ICF is an affordable, attractive driver, and you see that also going on in parallel. It doesn't get the same airplay that a scientific demonstration did, but it's also going on in parallel. And ICF, of course, has to bring all those things together. Omar.
Yeah, so there's a lot to unpack there. But there's what a lot of people don't understand is actually when you try to make a small uh, fusion target work, it's actually much, much more difficult than the large one. That's why
Yep.
you have the national security related targets that Mike was referring to from the Cold War that worked back in the 1950s versus what we have now, which took a lot more stress. The uh, the December 22 result was fantastic, but I think the way the hype revolving around that came out did a little bit of an injustice to kind of the rather steady progress that occurred the decade before that.
Right.
Uh, it's actually been very incremental progress from the time NIF was first completed. We started doing experiments to get to where we are today with these tremendous yields and getting more fusion energy out than fusion energy in. The reason why it looks so dramatic is fusion is a very threshold process. So basically, you don't see much action in terms of fusion yield until you hit the threshold, and then you get this explosive release of energy. And it took a lot of problem solving to work through the different technical issues we had to reach that threshold with what is a rather limited amount of energy that we have from our laser, despite it being the largest, most energetic laser system in the world. And Mike talked about gains. We got target gain, which you were just referring to, of about 4, which was the fusion energy out compared to the energy that went in with the laser. Mike referred to capsule gain. Think of the targets as a set of onion skins. You have the target, then the next layer in is the capsule, and then the next layer in is the fuel. Every time you move from layer to layer, you actually give up energy because the way the system works is we're trying to take energy that was deposited on the outside and concentrate it into the middle. Uh, Mike referred to capsule gains of over 30. We're actually also getting fusion fuel gains of many hundreds now. And again, the fusion fuel is the most central part of the target. So we're getting hundreds of times more energy out of the fusion fuel than we got in. But the first time we got more energy out of the fusion fuel than we got in was back in 2014. And that actually did make quite a few headlines in the press back then. And we had to restrain the hype at that time. But it's been incremental problem solving all along. And it's continued to be incremental problem solving since December 2022 that has allowed us to have these additional advances and increases in fusion yield. And that will keep going because there are a number of problems that still need to be solved. I could go into technical details if you wanted to hear about that, but every time we fix one of these technical problems, we can expect an advance in fusion energy production and learn a bit more about how to do this stuff better.
Yeah, the thing is, some of the incremental progress, not only understanding has come about, is improvements in target fabrication. So the targets have gotten better. Targets are, a major, issue for the success of ICF. And so there's been tremendous work done in improving target fabrication by companies like General Atomics and Livermore and Los Alamos. So targets have been a big deal, and the improvements of them has been essential for achieving ignition. And the other thing, which I'm an experimentalist, and so Omar is a modeler, and so I love diagnostics and measurements. You have to see what's going wrong to be able to fix it. And so the advances in diagnostics have been absolutely critical in the progress that has been done at NIF. So it's modeling and simulations, physics understanding, driven by, and then also driven improvements in target fabrication and the measurement technologies that goes along with it. So NIF is, it's all those things you have to do. And fusion energy is going to require all of those things too.
And we talk about reaching this goal of commercial fusion energy. What are the technologies that the community in this hopes to enable or see advance, such as laser diodes, high energy optics, fusion fuel, and things of that nature?
Let me go first, and then we're going. So first, we have to develop lasers that are both efficient and cost effective. And there's two classes of lasers that are being explored, and this goes back to the 90s. There are gas lasers called excimer lasers, and then there's a diode pump solid state laser. So both of these technologies, they both have their pluses and minuses, but they both have attractive. They both are attractive that they both should be pursued. And so it's not just diodes and other stuff. It's pulse power that has to be advanced. For both pulse power drivers and also pulse power for laser drivers. So we need the supply chain is diodes, gain material, pulse power technologies, capacitors and switches and the like, and optics. You need to have optics that can withstand the optical fluences on this at tens to million shots a day. So it's also those things that you have to do. So when we were doing NIF back in the 90s, we spent an enormous amount of money and time to develop the supply chain for NIF. NIF could not have been built with the supply chain that existed prior to our development. We had to develop a whole new ways of making laser glass, nonlinear optics, for frequency conversion that had to be developed or for NIF to be both affordable and to be done at a timescale that made sense. Those things have to happen with IFE. There's efforts going on, through the DoD and other places, but we need to, again, emphasize the supply chain needs for fusion. And of course, targets. We mentioned targets before. You have to learn to mass produce those. And there's been efforts in the past, but not on the level that is required to get to the point where you can make them commercially viable. Because you have to have them, in the end, you have to be able to produce them for less than $1 a target. And I'd be afraid to say what targets cost today, Omar. It probably costs more than Omar's annual salary, a target right now.
Only it's big. I'm kind of expensive these days, but
those are things. So for ICF, it's targets, it's driver technology, and the supply chain, with the driver technology that has to be emphasized more. And then, of course, tritium. There's going to be DT fusion requires lithium. And, one of the things we need to do is let the lithium industry, the mining industry, know that there is an opportunity other than batteries for lithium. Now, of course, you don't need the same amount of lithium for ICF as you need for batteries, but it's an issue that we have to get the supply chain. Let's go all the way back to the origin. So developing the supply chain for targets, fuels, and drivers is something very, very important to do. Omar, and then, of course, people, right?
Exactly. You have to have people that know what they're doing. It's taking a black box approach to this just isn't going to work. What a lot of people actually don't understand is the level of precision that's needed in things like targets and the level of precision that's needed in these lasers. And that the physics behind it is kind of rather simple. The laser in a way is a power amplifier. It sucks in electrical energy at the beginning over kind of a long period of time and then delivers it in a short burst, amplifying the power. What's less understandable to people who are not experts is the ICF targets are also power amplifiers. They take the energy from the laser and then they power amplify it by the time the energy gets into the fusion fuel. So the way an ICF system works, or an IFE system works, is you have two amplifiers, two nonlinear amplifiers stacked on top of each other. And that makes the end product extremely sensitive to errors that accumulate along the way because you kind of exponentiate the errors twice. So the reason why targets, as Mike kept bringing up, is so critical is just tiny little imperfections get amplified enormously by the time you're done, and then it doesn't work. The laser, tiny little imperfections in the temporal way you deliver the laser pulse, the cross timing of the lasers, a small difference at the beginning becomes a enormous problem at the end. And so all of these things have to be um, controlled to levels that are kind of beyond the experience of the average person, even like the average engineer. It's often the level of precision goes beyond the intuitive understanding of even some of the people who work on this stuff. And that was part of our frustration in getting things to work, just the level of engineering control that we had to apply to our system to get to these major milestones. On the NIF, we basically regularly touch it when we do our experiments, and that's a rate limiting. That's known. I mean, it was engineered to do that because that's the technology at the time. We knew that we were going to have to operate with damage in order to have any chance of success. But that's a constant problem for us where we kind of have to monitor and refurbish our laser system as we do experiments, and it's also rate limiting on how many experiments we can do. A fusion energy system couldn't possibly operate where it's constantly damaging itself the way we're doing it now. And so those are the optics advances, uh, and maybe redesign so that we aren't operating above a damage threshold constantly would be something that's needed for a fusion energy system. The targets, as I mentioned and Mike mentioned, require an incredible amount of precision in their construction, the smoothness, concentricity of, say, the capsule on the inside, really tiny little factors that are fractions of a percent matter. And that this is kind of a tension because usually to make things that are really precise and accurate costs money. But if you have to shoot, thousands or millions of these things a day, they can't cost that much money. And so there's a tension there between what we know is required for the physics and what's needed for it to be practical. And there's going to be some work that needs to be done to kind of find a solution that's consistent with both practicality and the physics. And it'll be interesting to see what that looks like.
I think, Joe, one of the other things important is that, as Omar said, the precision that you need, energy is one of the more forgiving aspects. And you still need the high precision, but the more energy you have, so you can begin to relax some of these things to a certain extent. I don't want to minimize that, but energy is a commodity. And the original proposal for NIF was 10 megajoules, but it was deemed to be unaffordable. And so we went to 2 megajoules, knowing there'd be a higher risk to achieve ignition, but it was something that we couldn't afford what the original cost was. So a higher energy laser, and you see some of the laser companies or some of the ICF companies are talking about more energy because that is a leverage on to address some of the challenges that Omar has talked about. But I think one of the other things important to note is that there are spin-off activities that happen with fusion. And we don't get enough airplay on that. One of the most miraculous things that we have today is the integrated circuit industry. The EUV lithography, which makes all of these very, very small chips. With critical dimensions, which are tens of angstroms. You think about 2 nanometer critical dimensions. That was invented by the ICF program. It doesn't get enough airplay. It was done back in the 80s. And Intel and others did things in this, but there's a lot of spin-off things. Laser technology is a big spin-off. I think some of the laboratory astrophysics. We do work in the laboratory now. Not just looking at X-rays, but actually understanding astrophysical phenomena, materials under extreme conditions. And as Omar said, you have both the laser, which is it concentrates energy in space and time. That's what it's a power amplifier. That's what it does, right? The explosion concentrates it even further. That's the other nonlinear process that Omar was talking about. And what NIF has achieved, Omar, you should say, what are the pressures in the fuel that NIF has achieved by these two nonlinear processes is quite remarkable. So, Omar, why don't you say what the pressures are with NIF?
It's about 2.5 times the pressure at the center of the sun. So we're talking about pressures on the order of 500 to 700 gigabars, which is gigabar is a billion atmospheres. 1 atmosphere is the pressure here at sea level. So, 2.5 times the pressure at the center of the sun. It lasts for a tiny moment in time.
Thank God.
But, that's an extreme condition, and it's a result of this double power amplification process of the laser and the ICF target working in conjunction with each other. And so that's quite remarkable. In a way, IFE systems are amplifiers in general.
Yep.
And but the technical challenge is we're trying to amplify the properties we want, like that enormous pressure, which is required to trigger thermonuclear feedback and very high energy generation, and amplify things we don't want, like all the things we don't have perfect control over. So that's basically the challenge of an IFE system.
And before I let you two go, my last question, it's going to be a tough one, probably impossible to answer, but how soon can my home be powered by fusion, if we're going to guess years?
All right, I'll say, I'll make a statement on this, of course, because I'm an optimist by nature. I can't help myself. Anyone involved in fusion has to be an optimist, right? So I think it is possible that we can have non-commercial viable pilot plants that put everything together, right? The driver, the targets, all the breeding of tritium, sometime in the late 2030s. And then a commercial plant within a decade after that. But it will require sustained, committed funding and persistence because it's not going to be easy. That's my own, and I think I mentioned before, Joseph, when my son was born 30 years ago, I'd said at that time he would see fusion in his lifetime. He'd either be 50 or 120, and he's now 30. So at that time frame, I still believe in that time frame. Omar, what do you think?
I kind of have a little bit of a joke answer, indirect answer to your question. In a way, your home is actually powered by fusion energy right now. So all the fossil fuels that we burn, that energy came from the sun, billions, millions of years ago, feeding energy into the plants and animals that eventually became our fossil fuels. And if you have any wind or solar right now, the winds are pushed by solar energy. That's fusion. The sun is fusion energy. So most likely you're powered by fusion right now. That's not the answer you want. You mean the other fusion, the people-made fusion. And I agree with Mike. It's with commitment and dedication. We're talking about decades before it's going to be energy on the grid. I think anything more optimistic than that is not realistic. And without commitment, it's going to be longer. So,
yeah.
Right,
And
well,
I
sorry,
think the
go
other
on.
thing is, there are other applications of ICF. I mean, the national security application is something that is important, and that's benefiting right now. That's going on with NIF, and then as we develop IFE down the road, that also will benefit. The national security applications will continue to evolve as we make more capable fusion systems, ICF systems. That's an important thing also because it gives again, like we were talking about before, why this is a national security issue. I mean, China is building a laser, larger than NIF for national security, but energy as a adjacent market. ICF energy is the market, and adjacent market is national security. And because of the uniqueness of making matter under these extreme conditions that happens in only a few places.
All right. Well, Mike Campbell, Omar Hurricane, I appreciate you so much for the insight, and we'll keep track closely to see what develops in fusion and to see what NIF gets up to. Thank you again.
And thank you for your questions, Joseph. They were very good questions. Let's make fusion work, right?
Absolutely.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.